My name is Anthony Basocco, and I'm a sophomore electrical and computer engineering student at Northeastern University. This video is my SpaceX Fall 2016 internship application, and the project that I'd like to talk a little about today is a practical notification system in order to detect sudden ionospheric disturbances.
The goal of my project is to detect sudden ionospheric disturbances. One example of a sudden ionospheric disturbance is a solar flare. A solar flare is the sudden release of high-energy particles from a sunspot caused by the built-up magnetic energy in the solar atmosphere. One negative effect of a solar flare is its ability to damage vital communication systems and power plants. One example of this occurring was in 1989 in Quebec, Canada, where Quebec's hydroelectric grid was damaged for over 24 hours and cost over $2 billion in damage. Another larger example was in 1998, the Galaxy 4 satellite, which cost for over $250 million in damage, causing for the satellite to lose its telecommunication with Earth, wiping out pager traffic, TV stations, radio stations. As we can see, these two examples are the both large negative effects of a solar flare, and therefore we need some sort of prediction mechanism in order to defend and protect against them. Two current methodologies used to predict solar flares are satellite-based systems and machine learning-based systems. Where my system fits in this overall half between these two is I'm trying to create an inexpensive system create the satellites and an accurate system. So I'm trying to just create to lower the startup cost for trying to create a solar flare notification system. How my flare notification system works is using very low frequency radio signal propagation. Very low frequency waves, based on the conditions of the atmosphere, whether a flare is present or not, propagate differently. For example, when a flare is present, they propagate off the D layer and come back with almost 100% its received signal strength. Although in a typical situation day to day when there's no solar activity, it will bounce off the E layer, causing for a larger path, coming with less reflection off the E layer. Due to this difference in reflection, there's a difference in received signal strength. At the end where we bounce off the D layer, we have a larger signal strength. Due to this, we can determine if flare is present or not due to the difference in received signal strength. So how do we get all these different VLF waves? They come from VLF wave stations from around the world that are being used to transmit with submerged submarines. This is an example of some of the stations out there currently. The one that I mostly used was Cutler, Maine, NAA, which transmitted at 24 kilohertz at 1,000 kilowatts. This station was close to my geographic home and allowed me to get the best signals in order to determine if a flare was present or not. So the first thing I had to detect all these flares and obtain these signals was building an antenna. I built a loop antenna with two wood cross beams with 50 turns of copper enameled wire. These signals then went into a preamplifier, which took these signals that were minuscule in voltage and preamplified them up to a level readable to a sound card. The sound card then converted these analog to digital signals, and I then filtered them using a finite impulse response filter. This finite impulse response filter then removed the signals that were outside of the station bandwidth, and once I did that, I performed a fast Fourier transform, which was able to find the different points at which the stations were occurring. So this is the first plot that you're going to see. This is the data that came straight from the antenna to the preamplifier and was digitized. You can see it's a little bit noisy, and you see some recurring events that are due to 60 kilohertz spikes due to noise, due to power lines. Now, after that, I filtered it using this finite impulse response filter, and you can see I removed those spikes, and it's much more of a clean signal now. This signal I was then able to perform the fast Fourier transform on, and doing that, I was able to find the different VLF wave stations that you can now pick out that we saw before in the map on the bottom left. What I would then do is I would take one of these frequencies and I would plot that one signal against time. After this, I would then create a large plot of these against time, and I could then recognize different features in the data. There are currently 4 different features that are in the solar flare data that you're going to see. Nighttime data, which is mostly noisy, and where you're not going to detect any flares because you're not facing the sun. Therefore, you won't be affected by them. You have the sunrise and sunset phenomenons, which occur due to a large inrush of charged particles due to the sun hitting that side of the Earth. And then you have solar flares, which are represented by large peaks in the data and large spikes. So how do I detect these flares? I use a threshold and grading algorithm. what I did before all of this was I got 30 days worth of solar flare data, confirmed using the GOES satellite, and I averaged all the gradients of the flares that occurred. And using this gradient, I then now had a measure of determining when a flare was present or not. In addition to this gradient, I also used a threshold value. So if the function that I was looking at, the plot that we had a the function value was greater than the threshold value, and the function gradient was greater than the threshold gradient. With these two conditions, I would then trigger for a notification. I had two current notification systems that were out. I used a Twitter-based platform and a text messaging-based platform, and both these platforms were able to relay the information with plots, data, and different signals that you would need to determine should I take action against this flare or what you would need to do. This now is an example of playing back data that I had in a real-time based fashion, except accelerated, so that you could see the different events that were occurring. So this program would run on my computer and it would take the data in, and when a flare occurred, it would stop, it would see flare detected, it would take a picture of it, and you get a magnitude-based plot seeing red, dangerous flare, blue, not as dangerous, not a flare. That data was then relayed over to the Twitter-based platform, which you'll see now, and you'll see two notifications which would give you the plot, time of occurrence, and what the signal strength was at that point, which are vital information in order to know what you want to do next in terms of preventative measures. Once that occurred, then the program would run on and on, and it would continue to look for flares. In conclusion, my program had an 87% success rate in determining flares, although 100% in determining the ones that would damage Earth's telecommunication systems. The ones that were small were too small to damage Earth's systems, so they were not included in that 87%. Overall, my system gave an hour and a half pre-notification time before the maximum intensity of the flare. The program was tested for a period of 10 weeks, and my system altogether cost about $120 to build. Now, if we look at the comparison between my investigation and the GOES satellite, we can see the two flares in the GOES satellite at the 12 o'clock mark and around the 2,000 hours mark. And looking at that, we can also look at my plot, and we see these same two flares, showing that my system also can give the same results. So some real-life applications of this was for early detection systems for power plants, railroads, wireless communication systems. In addition to that, amateur radio operators are interested in this for the propagation effects that we may want to look at for our radio waves. And some future projects I was looking into in the future now is optimizing the antenna, trying to get possibly 2 or 3 antennas and trying to beam steer things and try to figure out nulling out different signals in different directions to get better signal strength. That's it. Thank you for your time.